Okay, guys, so as we talked previously, we're going to do now an example in which we are going to determine the capacity of this reinforced concrete beam, and which is a simple supported reinforced concrete beam over a 14 feet span, sorry. And the cross section of the beam is a 20 by 12 inches. It's a 4,000 psi concrete, right? And the section has four number eight reinforcing bars, okay, in which the distance d from the top fibers to the center of mass of the reinforcements is around 17.5 inches. We're using also a 60 ksi steel. And the exercise want us to determine using nominal stresses and forces how much uniform load can this section support. Okay, so this exercise is quite simple because what we want to do is how much load Q can be carried by this section. And what we can do is, if you remember from your your structural analysis class, you will remember that the bending moment for simple supported beams has a parabolical shape in which the maximum moment is going to be the load, distributed load, times the span square divided by 8. Okay, so the main idea of the exercise is we are going to say that the bending moment acting on the beam is going to be equivalent or smaller than the nominal resistant moment. So theoretically speaking, we're just going to do this. And once we determine the bending moment, we are going to isolate Q, and Q is going to be smaller than 8 times the bending moment over the span square. Okay, so that's the main idea. Let's start this exercise then. I put here some steps. The first step is to determine the area of reinforcements, because without the area of reinforcements, we can't determine the position of the neutral line. If you remember the number 8 reinforcement, the cross-section area of one reinforcement is equals to 0.78 square centimeters. If you don't remember this, it's quite simple to determine. The area of any reinforcement equals to the number of reinforcements bars times the area of each reinforcement, which is calculated by pi, the diameter of the rebar to the square, divided by 4. Okay. And Yuri, how much is the diameter of the number 8 bar? Usually for the US metric systems, usually it's that number divided by 8. So the bar diameter of the number 8 is 1. If you get the number 6 bar, for example, 6, you divide it by 8, and you would have the diameter, the nominal diameter, which is 0.75 inches. If you go back to the table here, as you can see, 0.75 inches to square. Okay. Most designers, whenever we are doing our jobs, we tend to memorize the cross section area of some reinforcing bars. But here I want you guys to learn how to do it. So in this case, the number of bars equals to 4. The diameter, as we saw, it's 1 inches. It's 1 inch divided by 4. This is 4 multiplied by, well, pi divided by 4, 0.785, as we saw here from memory. This value times 4 equals to 3.14, around 3.14 square inches. Okay, so now that we know the area, we can determine the position of the neutral line. Okay, from the equations that we saw from the previous video, you can check here the equations for the position of the neutral x and for the nominal bending moment. So applying the equations is quite simple. It's S times Fy, so the force of the tension reinforcements, multiplied by 0.85 because the concrete is over 8,000 psi, multiplied by F prime C times the width of the beam. The area of the reinforcements we already used. This is a 60 ksi still. Here, the F prime C, it's a 4,000 psi. So its ksi is just divided by 1,000. And then you have the width of the beam, which is 12 inches. Guys, it's important to always check the units. So the area is square inches. The Fy, the steel strength, it's in ksi. Ksi equals to kip per square inches. Okay. F prime is also in ksi. B is in inches. All right. So ksi cuts with ksi. Inch will cut with square inch. So C and A, their unit is going to be in inches. Beta 1, guys, just remember this factor does not have units. So this value here is going to be in inches. Let's divide here. So we have 3.14. Let's multiply times 60. Then divide by 0.85. Then divide by 4. And divide by 12. This equals to 4.19. 619, sorry. Okay, so that's the position of the neutral line. Actually, this is the depth of the stress block. The position of the neutral line is bigger, so we divide this by 0.85. So the little c divided, let's divide this by 0.85. It's 5.43. 5.435 inches. Okay. Now that we have the little c, we have also a, and we have the area of reinforcement. We can calculate the bending moment. However, it's important to remember that we need to assess if we have the condition of ductility, okay? We need to assess if the strain in our reinforcements is going to be bigger than the yielding reinforcements. So we calculate the yielding reinforcements. Usually we memorize this, but let's do it one time here. So this is a 60 ksi steel, and the modulus of elasticity of regular reinforcements usually tend to be 29,000. Depends on the guy who's the catalog of your supplier. Remembering this guy is in KSI, this guy is also in KSI, so it's going to be cut, and the strain is unitless, so there's no unit, just to remember. So 60 divided by 29,000 equals to 0.00206. By 1,000, which is the unit symbol that we usually use, this equals to 1 over 1,000, equals to 2.06. Okay. To determine the strain in the reinforcements, just remember the equation that we did by triangles similarity. We just use this equation. So it's the deformation and the ultimate deformation of concrete, 0.003. Usually I use 0.0035, but this depends on the literature that you're using or the code requirements. For ACI, I think they use 3 per 1,000. Okay. The exercise gave us is 17.5 inches, which is the position from the top of the beam, okay, to the center of mass of the reinforcements. And c, little c, which is the depth of the neutral line, which is 5.435. Right, if we calculate this, and then divided by 5.435, and this, let's multiply it by 0.003. All right, 0.00665, which is around 665 over 1,000. So this guy here is bigger than the yielding strength. That means that this this is true. So the yielding reinforcement, the reinforcement will yield. So it's okay. All right. So this is important. Now that we know that the steel will yield, we can just calculate the nominal bending capacity, which is the equation that we did in the previous video. So it's right here. Just remember, is the force times the lever arm. Okay. The tension reinforcements we calculated, it's around 3.16, 3.14, 3.14. The strength of reinforcements 60 ksi. The 17.5 A we calculated as well. It's 4.619 over 2. Okay. And guys, it's also remember to check the units. This guy here, it's in square inches. This guy here, it's KSI. And these guys here are going to be in inches. KSI is equals to kips per square inches. This is going to be cut with this. And then you're going to have kip times inches. So your answer here is going to be kip inch. Okay, let's calculate this for a bit. We have 4.619 divided by 2. This we subtract to 17.5. And then we multiply by 60. And then we multiply by 3.14. 28, sorry. 2.861. All right. Just remembering, guys, that sometimes we don't usually use these units, kips per inches. We tend to usually use kips per feet and kips per foot, sorry. And what we do to transform inches to feet, to a foot, we just divide it by 12. So this value here, I'm just going to divide it by 12. To 238, around in 385 kips per foot. All right. So this is how much bending moment this section can support. So now in terms of loading, as we said in the beginning of this exercise, we know that the loading Q has to be smaller than we did the equation here, 8 times the bending moment. So 8 times the bending nominal moment divided by the span square. Okay. Calculating this, let me just erase this for a bit. We have here, it's going to be 8 times 238.5 divided by 14 to the square. Check again units. This guy is in kips per foot. This guy is going to be in feet square, and this is unitless. So foot cuts with foot, and then you're going to have kip divided by foot, which is right here. Usually that's the unit that we assess uniform distributed loads. All right, so I'm going to multiply this by 8, sorry, and then divide it by 14, and divide it by 14, 9.73. All right, that's usually That's the amount of, I'll just put this, oh, come on, Yuri. So this is would be the maximum amount of load that this bin would be able to support. So imagine that you're assessing an old house or a garage, and you want to know if your garage will support the weight of the cars, for example. So that's the way you that you can do it. Okay, guys, it's also very important to assess your calculations because we did it here by hand using the calculator of the computer, which is not good. So I developed an Excel sheet to run these calculations. Just gonna raise this, and this. Okay. So the Excel spreadsheet looks like this. Okay. I designed for simply supported and doubly reinforced beams, which is going to be the next topic. And everything that we saw in the previous videos are summarized here. So as you guys remember, this section has 20 inches by 12. And I'm just going to put here the number of reinforcements, which is number of bars 8, and we have 4 numbers bars. The PSI, the concrete is for 1000 PSI, and the steel is a 60 KSI grade steel. Okay. And here I uploaded a nominal cover. You can change that if you like, or you can also change the D here if you like. I also put here the coefficients beta 1 and alpha. If I change, for example, 5000 KSI, it recalculates 9000 KSI, it recalculates both. Okay, so you can also change that if you like. The number of bars goes all the way from 2 to 218 US units, and the number of bars are here. So let's see what this Excel spreadsheet gives us. Here also it calculates the D based on the transversal reinforcements. We're going to talk about this soon. You can ignore here and just change here if you like. But again, it calculates the area of reinforcements, 3.14, okay? Calculates the yielding strength, which is around that number that we calculated. And here it checks the A, calculates A 4.619, something about this, and the C2, the depth of the neutral line, which is around, and also calculates the strain, the stress, and the strain in the reinforcing steel. If it gets blue here, it means that it is above the yielding strength. Okay. If that value would be over, or if you had a section with a lot of reinforcement, let's just say 18, for example, this would not be the case. So your section wouldn't be ductile. Okay. Continue here. It calculates the force, the section of the forces, and here calculates the bending moment. All right, considering. And since this is a section that is tension control, the penalty factor that we talked about, the ACI, it's around 0.9, which is good. So it is okay. All right. If you like to have access to this Excel spreadsheet, you can just email me, and I can sell this to you. It's just I will give the information below in the comments. So guys, this is really cool. It's important for you guys to have these types of Excel spreadsheets. This was easy to calculate. If you have any questions, just please put in the comments below, and I hope to like this exercise. The next video, we're going to talk about the sections with double reinforcements that I'm doing right now. Okay, so see you soon.